exothermic reactions lose energy in favor of the surroundings. Heat is being released. And by convention, we use a negative number to show this. So when you see an enthalpy value, which is a negative number, that means the reaction is exothermic. And that sign convention comes from the 19th century because that energy release, it was in the form of heat, was seen as negative because your energy is losing energy in favor of the surroundings. So that's where the minus comes from. It's just a symbol convention. If we draw what we call an energy diagram, like the one I've got in the screen, let's see what it tells us. On here, we represent the energy of the reaction in terms of the enthalpy. And here we represent the progress of the reaction. So from the reagents to the products. If you have a reaction which is exothermic, means that energy is heat. Energy is being released in the form of heat. What does that mean? It means that your reagents, your reactants have enough energy that they can make the products and give out some of that energy in the form of heat. So the enthalpy of the reagents is higher than the enthalpy of the products because they have enough energy to make the products. The reagents have enough energy to make the products, and there is a certain energy left over that is being released in the form of heat to the surroundings. This is how the energy diagram of an endothermic reaction looks like. In an endothermic reaction, the value for delta H, for the changing enthalpy, is a positive number. And that's by convention, because in the same way that exothermic reactions, it was seen as they lose heat, they lose energy to the surroundings. In the case of endothermic reactions, because they need heat to happen, it's considered that reactions gain energy from the surroundings. For that's why delta H is seen as a positive, is written as a positive number for an endothermic reaction, because it's seen as an energy gain. So if I draw the energy diagram of an endothermic reaction, in an endothermic reaction, the reagents on their own have not enough energy to make the products. To make those products, they need an input of energy in the form of heat. And that's what this diagram is trying to represent. And that's what the delta H is there. The reagents, that delta H is the amount of energy needed by the reactants to be able to make the products. So heat is going into the reaction. So if we go back to the reaction we looked at a couple of slides ago, the hydrolysis of urea, and we look at the enthalpy of that reaction, 133.6 kilojoules, could I ask you to stop the video and draw an energy diagram for that reaction specifically? Could you draw an energy diagram for that reaction? Stop the video now, please. Okay, so what do I do now? Well, first of all, I look at the changing enthalpy and I see it's a positive number. That tells me that this reaction is going to need heat to happen. It's going to absorb a certain amount of energy in the form of heat from the surroundings for the reaction to take place. That means that my reagents energy is lower than my product's energy, and that gap is what that enthalpy is. So when I draw my energy diagram, I put here enthalpy, and I put here progress of the reaction. And then I draw a line, and I think, okay, well, these are going to be my reagents. And my reagents are the urea, NH2 plus H2O. And my products are going to be CO2 and 2 moles of ammonia, and they are going to have a higher energy than my reagents. So I draw here CO2 and the 2 moles of ammonia. And this, delta H, is plus 133.6 kilojoules. So I take the general diagram of an endothermic reaction and I draw it with the data for the reaction I'm interested on, the change in enthalpy and the specific reagents and products involved in that particular reaction. Once we have the value for delta H, then we include it in the equation. And this combination of the chemical reaction, in which it shows you the chemicals you're using, the chemicals you're producing, the ratios of the chemicals, and also the state of the chemicals. Here I can see that these two reagents and the products are all in gas state, and we have a value of the enthalpy for that reaction. The combination of that enthalpy and the chemical equation is what we call a thermochemical equation, and they are associated. That reaction, which is the combustion, the reaction of the reaction of ethylene with hydrogen to produce ethane, is an exothermic reaction because of the negative sign of delta H, and it releases 137 kilojoules. And that, as a whole, the equation and the change in enthalpy, is what we call thermochemical equations.